Okay, so let's continue. So if we consider the real size of the elements, so we can say at the two end zones, we have the rigid end zones, or however, that's the assumptions. At the end zones, the moment of inertia and the sectional area, they are both close to infinity. Okay, so how can we analyze a problem like this one? And first, when we derive the element stiffness matrix K, we use the EA divided by L, 0, 0, negative EA divided by L, 0, 0. Also, we have the 12 EI L cubic divided by L cubic. And for the L, usually we say that's the length of the element. Okay, so in the previous derivations, we can say they are the square root of the xb minus xa square plus yb minus ya square. Okay, so we can calculate from the input nodal coordinates, we can calculate the length of the element. And the xa and xb, xa and ya, they are the nodal coordinates of the first endpoint. And the xb, yb, they are the nodal coordinates for the second endpoint. Okay, and in the previous derivation, we didn't consider the rigid end zone. So we will say the input, the sectional area, the input moment of inertia, they are valid from the first endpoint to the second endpoint. So we assume for the entire length, they have constant sectional area and the moment of inertia. Okay, so that's the previous derivation. We didn't consider the real size of the elements, so we didn't consider the two end zones. Actually, they have much larger moment of inertia and much larger of the sectional area. We didn't consider for these. Okay, now if we consider the rigid end zone, the rigid end zone, okay, right now we try to consider the two end zones. They are the so-called rigid end zone. We can say here is the node point A to node point B. Let's say we have the A prime and the B prime. And we have the L, which is from the A to B. Also, we have the L prime, which is from A prime to B prime. Okay, and from A to A prime, they are the that's okay. So we have the from node point A to A prime, they are considered as the rigid end zone. And from the B prime to the B, it is another rigid end zone. And from the A prime to the B prime, it is the constant cross section. And that's the related the input I and A. Okay, so the users need to input from the column phase to the column phase, the sectional area of this one. Okay, so in this case, first we will try to add two middle node point. Okay, so let's say okay, from the A prime to the B prime we have. So we can calculate the K prime first. And we need to use the length, not from the point A to the point B. We need to use the L prime. Okay. So what is the L prime? L prime is equal to L minus A prime minus B prime B. Okay. So that's the length of the element minus A prime, the length between the A and A prime, and minus B prime B, the length between the point and B. So here we need to use the L prime. So we can calculate the K prime since from the node point A prime to node point B prime, we have the input I and A, which can be applied to this. Okay, so we will calculate the K prime first. Actually, here we consider so we have the K prime multiplied by the UA prime, V A prime, theta A prime. That's the member influence. And A prime. Okay, so as long as I add the prime, it means it is the element stiffness matrix which can be applied from the point A prime to point B prime. Okay, it cannot be applied to the entire length of the element. Okay, that's the K prime we can calculate, and then we will study the displacement relationship. Actually, you can say we are trying to derive the constraint. Okay, what is the, actually you can say what are the constraint equations for point A to point A prime. Remember, we assume the moment of inertia and the sectional area close to infinity. So you can say since the A approach to infinity, then you can say the UA prime should be equal to the UA, And remember that's the local coordinate, that's the local coordinates from the A to the B. And although I hate to add the prime again, but remember, where we are talking about the U displacements, they are referred to the local x prime axis. But I have already used the prime to refer to the internal part, the center part of the element. So I didn't add the prime for the displacement component. But remember, here we are talking about the UA and the UA prime. They are the actual displacement for this element. Okay, so let's see. Okay, so since we assume the A approach to infinity, therefore we have the actually the actual deformations for this part can be neglected. So the actual displacements, they should be same. Okay, so that's the first equation. Also remember, the I is infinity. The I is infinity means we cannot have any kind of the bend of the bending of the center line. So if we have the VA and the theta A for this point, what will be the A prime? Since it is a straight line, so the theta A prime should be equal to theta A. Okay, since you cannot bend, since you cannot bend for this part, it is always rigid and continuous. And for the right, initially the theta A prime is also true for the left end. However, we could have the change of the theta. But from point A to the point A prime, the theta will not be changed since we have already assumed the I approach to infinity. So the theta A prime should be equal to the theta A. And what will be the VA prime? Times theta A. Okay, so we can get we can put them in a matrix form. So if we put these three equations in the matrix form, we can say okay, so that's the transformation matrix. That's the transformation matrix between the for the two points from the A to the A prime. If we know the nodal displacement at point A, then we can calculate the related nodal displacement at the A prime. Okay, I will take a break here and continue with the next hour.